Hi dear students, welcome to today's topic. Today we are going to discuss the topic electrolytic conductance and kohlras's law. It is the fourth module of the chemistry for process engineers 2. In this video, we are going to discuss what is the basics of electrolytic conductance and what is kohlras's law and what are the important applications of kohlras's law. Before going to the details of conductance and kohlras's law, what do you mean by electrolyte? And electrolyte is a substance, as we know, electrolyte is a substance that produces an electrically conducting solution when dissolved in polar solvents like water. The electrolyte dissolve and they are separated into cations and anion, which disperse uniformly through the solvent. And electrolyte is such a solution that is neutral in nature. There are two types of electrolyte, strong electrolyte and weak electrolyte. Strong electrolyte, they are completely dissociated. That is 100% dissociation in solution, while in weak electrolyte, only 1 to 10% they are partially dissociated state. Another difference between the strong electrolyte and weak electrolyte, the principal species present in strong electrolyte is ions, while in weak electrolyte is the unionized compound itself act as the principal species. Strong electrolyte is categorized into three: the strong acid, strong base, and salt. The strong acids like HCl, HNO3, bases like sodium hydroxide, potassium hydroxide, then salts like NaCl, KBr. But weak electrolyte, there are two types: weak acids and weak bases. Acetic acid, carbonic acid, phosphoric acid, are the examples for weak acids. Ammonia, pyridine, etc. are the examples for weak bases. What do you mean by conductance, or what do you mean by conductance of the electrolyte? Conductance is more appropriate for the description of electrolytic solution, and conductance is the reciprocal of resistance, or conductance is equal to 1 by resistance, or it is 1 by R, and it is expressed with unit Siemens, or 1 Siemens is equal to 1 ohm raised to minus 1. The conductance of the solution is the sum of conductance of solvent and the solute. And the conductivity or specific conductance is equal to conductance into cell constant. And that is the conductance is from the basics law, that is Ohm's law is the basics of all the conductance measurement, all the conductivity terms. And what is Ohm's law? That is voltage is proportional to current, or V is equal to IR. And then what is R? R is a resistance, or R is equal to rho into L by A, where rho is the specific resistance or resistivity. It is a characteristics of a material, and L is the length of the conducting material, and area is the area, A is the area of cross section. Rearranging this equation, we get resistance is equal to resistivity into cell constant, that is L by A. That is a length by area of cross section. That factor is known as cell constant. Or rearranging that equation, 1 by resistivity is equal to 1 by resistance into cell constant. What is 1 by resistivity? That is conductivity or specific conductance. That is equal to conductance into 1 by R is the 1 by R is the conductance into cell constant. That is conductivity or specific conductance is expressed in terms of ohm raised to minus 1, that is a unit of conductance, and cell constant, that is L by A, that is centimeter raised to minus 1. Then next is equivalent conductance. The conductance is of an electrolyte solution containing 1 gram equivalent of electrolyte, and that is known as equivalent conductance, and or that is equal to expressed in lambda, or that is equal to K into V, where K is the specific conductance, or equivalent conductance lambda is equal to K into 1000 by N, where N is the normality. that is equivalent conductance, that is equal to specific conductance of the solution and the volume of the solution that is the important point, that containing 1 gram equivalent of the electrolyte, and that is the of a solution containing 1 gram equivalent of the electrolyte. For such a solution that possesses a conductance, and that conductance is known as equivalent conductance. And another conductance that is molar conductance. What do you mean by a molar conductance? It is the total conductance of all the ions produced by 1 mole of an electrolyte present in a definite volume of the solution. And that is known as molar conductance. And molar conductance lambda m, that is expressed denoted as lambda m, that is K K into 1000 by m, where kappa K or kappa is the specific conductance into m is the molar concentration of the solution. That is, molar conductance is equal to specific conductance into 1000 divided by molar concentration of the solution. And the unit of molar conductance is ohm raised to minus 1, centimeter square, and mole raised to minus 1. Next, we are going to what are the important factors affecting electrolytic conductance. There are three main factors that affect electrolytic conductance. One is nature of the electrolyte, second one is temperature, and third one is concentration of the electrolyte. Then, what is meaning of nature of the electrolyte? How nature of the electrolyte affect the conductance? The conductance of the electrolyte depends upon number of ions present in the solution. Therefore, greater the number of ions in the solution, greater is the conductance. It is strong electrolyte dissociate completely into the solution. That's why the strong electrolyte possesses high conductance. On the other hand, weak electrolyte dissociate to a very small extent and gives lesser number of ions in solution. Therefore, weak electrolyte have low conductance. That's the main difference between strong electrolyte possesses high conductance and weak electrolyte possesses low conductance. Another factor is temperature. The conductivity of an electrolyte depends upon temperature. With increase in temperature, the conductivity of the electrolyte increases. And third factor is concentration of the solution. And the molar conductance of electrolytic solution varies with the concentration of the electrolyte. That is, molar conductance of electrolyte increases with the decrease in concentration or increase in dilution. This is due to the fact that increase in the degree of ionization, the molar conductance increases with the decrease in concentration or increase in dilution. Molar conductance of strong electrolyte as well as weak electrolyte increases with the decrease in concentration or increase in dilution. Those are the three main factors that affect electrolytic conductance. Next, we move on to variation of molar conductance with dilution. What happen if we increase? Then what happen if we change in the concentration with? Then what happened to its molar conductance? The molar conductance of weak electrolyte and strong electrolyte increases with the dilution and attain a maximum value at a particular stage of dilution. This stage of dilution is known as infinite dilution, or the stage of infinite dilution can be considered as a stage of zero concentration. For example, we draw a graph on the y-axis, that is the molar conductance, on the x-axis, that is square root of concentration. That is how we can find the molar concentration at infinite dilution. In the case of strong electrolyte, if we plot a curve, molar conductance is to square root of 3, it is linearly proportional to the concentration. That is, molar conductance of strong electrolyte is linearly proportional to the concentration, but it is not linearly proportional in the case of weak electrolyte. That is, for weak electrolyte, the degree of ionization increases with the dilution, The number and mobility of ion increases, and as a result, molar conductance increases in the case of weak electrolyte. But for a strong electrolyte, since the ionization is complete, there is no increase in the number of ions with the dilution, but the mobility increases with the dilution, and that's why molar conductance is increases with the dilution. That is the case of strong electrolyte. That is a strong electrolyte, the mobility of ions increases. That's why the conductivity, molar conductance increases with the dilution. Then how we can, when the concentration approaches zero, the molar conductance of the solution is known as limiting molar conductance or conductance at infinite dilution, and that is represented as lambda m zero. Then, how we can find the molar conductance at infinite dilution for strong electrolyte? That first we consider for a strong electrolyte. That is, upon concentration, the molar conductance increases upon dilution. For a strong electrolyte, the molar conductance at infinite dilution or lambda m0 can be determined by extrapolation method. The solution of different concentration are prepared and the conductance is measured, and it can be plotted against its square root of C. For example, here two strong electrolytes are there. One is HCl and another one is KCl. It is two strong electrolyte is there. That is in the first curve. And we are measuring its conductance. We get the straight line when we plotted our conductance against the square root of C. Then we extrapolate that to zero, concentration zero. Then we get a value, and that is known as molar conductance at infinite dilution or zero concentration, or lambda m0 for HCl and KCl, or any strong electrolyte. We can able to find the molar conductance at infinite dilution by extrapolating molar conductance against the square root of C graph. But in the case of weak electrolyte, that is molar conductance, we plot a graph. In the second graph, that is for acetic acid, CH3COOH. The graph plotted between molar conductance is not a straight line. That is an important point. In weak electrolyte, that is molar conductance versus square root of C, is not a straight line. With lower molar conductivity and lower degree of dissociation at a higher concentration, which increases steeply at lower concentration. That's why there is no the limiting molar conductivity cannot be obtained by extrapolation of molar conductivity to zero concentration. Then how we can find the molar conductance at infinite dilution for a weak electrolyte? For that one, we are using one famous law that is known as kohlras's law of independent migration of ions for determining limiting molar conductance of a weak electrolyte. Then, what is kohlras's law? Kohlras's law states that the molar conductance of an electrolyte at infinite dilution is equal to the sum of conductance of all the ions, anions and cations present in the solution. Or at an infinite dilution, each ion of an electrolyte make a definite contribution towards the molar conductance of the electrolyte, irrespective of the nature of ions associated. That is, the molar conductance at infinite dilution lambda m0 or lambda m infinity is the sum of molar conductance of all the ions present in the electrolytic solution, that is equal to lambda plus infinity plus lambda minus infinity, or lambda 0. For example, lambda 0 of acetic acid is the sum of lambda 0 of CH3CO minus ions and lambda 0 of H plus ions, and that is known as kohlras's law. The molar conductance of electrolyte at infinite dilution is equal to the sum of conductance of all the ions present in the solution. And then what are the important application of important application of this kohlras law. Main application is, as we already discussed, that is determination of molar conductance of weak electrolyte. That is, what is molar conductance of at infinite dilution? We can easily analyze or easily determine the molar conductance of weak electrolyte by using this kohlras law. But according to kohlras law, at infinite dilution, the molar conductance is the sum of all the ions present in the solution. Then how we can determine the molar conductance for a weak electrolyte? Let's take, for example, we take molar conductivity of acid CH3COH can be calculated by kohlras law. According to kohlras law, the molar conductance of CH3CHOH is the sum of molar conductance of CH3O minus plus and lambda 0 H plus. That is taken as equation number 1. Then we can find the molar conductance of CH3COH and CH by using a strong electrolyte like sodium acetate, HCl, NaCl, etc. We take first is taken as molar conductance of sodium acetate CH3COH. According to kohlras law, it is the sum of CH3CO minus plus Na plus. In the case of HCl, the sum of H plus and Cl minus ion. In the case of NaCl, it is the sum of Cl minus and Na plus ion. Then our aim is to find the molar conductance of CH3COH. For that one, we simply add equation 2 plus equation 3. It is sodium acetate plus HCl, molar conductance of sodium acetate plus HCl. Then subtract equation 4 from that one. Then we get, that is lambda 0 CH3CO minus plus Na plus lambda 0 H plus lambda 0 Cl minus of lambda 0 Cl minus lambda 0 Na plus. And rearranging that one, that is lambda 0 Cl minus cancel, Na plus cancels. So we get lambda 0 CH3CO minus plus lambda 0 H plus. That is our aim, or in this way we can find the molar conductance of a weak electrolyte by using kohlras law. This is another example we can do yourself to find the molar conductivity of NH4OH. Another application is determination of transport number. That is transport number T plus or minus is equal to lambda plus or minus 0 by lambda M0, where lambda M0 is the molar conductance at infinite dilution. We can, later we can go into the details of transport number. Next, another application is to find the degree of dissociation of a weak electrolyte. Kohlras law can be used for determining the degree of ion dissociation of weak electrolyte at any concentration. For example, if lambda C is the molar conductance of electrolyte at concentration C and lambda 0 is the molar conductance of electrolyte at infinite dilution, then degree of dissociation alpha is equal to lambda C by lambda 0. In that way, we can find the degree of dissociation by using kohlras law. Another application is to determine the solubility of a sparingly soluble salt. For that one, we take the sparingly soluble salt like HCl, silver chloride, taken as the example. The solubility of a sparingly soluble salt in a solvent is quite low. Even a saturated solution of such a salt is so dilute that it can be assumed to be as an infinite dilution. Then molar conductivity of sparingly soluble salt at infinite dilution can be obtained from the relation lambda is equal to kappa, that is specific conductance into 1000 by M, or M is the molarity of the solution. Then how we can find M, or molarity, or concentration? First we find a saturated solution taken in an electrolytic cell and find its conductance. Then if the electrolytic cell has a cell constant, then multiply that conductance with the cell constant, then we get the value kappa. That is, what is specific conductance is the product of conductance into cell constant. Then substituting, and lambda is the value that is known as lambda is the infinite molar conductance at a infinite dilution for a sparingly soluble salt. This lambda can be analyzed or determined by using kohlras's law. Then rearranging that equation, we can find molarity of a particular solution using the equation lambda is equal to kappa into 1000 by m. These all are the important applications of kohlras's law. And that is all about electrolytic conductance and kohlras's law. Thank you.